Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this is the next video in our series about the analysis of variance, or ANOVA, and more specifically, the two-way ANOVA with replication. This is also called a two-factor ANOVA. Now, to make the topic more manageable, I've divided the video into several parts. In part 1, we covered the basics of the two-way ANOVA. Here in part 2, we will discuss the graph of marginal means. These are sometimes called interaction graphs, even though no interaction may be present. So in our last video, we took an in-depth look at the basics of the two-way ANOVA. As with many visual tools, marginal means graphs allow us to visualize the characteristics of each factor and any interaction that may be occurring between them. We will learn how to construct and interpret marginal means graphs, and then compare the graph to the actual output from, in this case, SPSS. So this video offers a solid, comprehensive, conceptual foundation of two-way ANOVA and interactions, using an example problem with illustrations and graphics. So if you are new to ANOVA, or are still trying to figure out exactly what it is, this video is for you. So, sit back, relax, and let's go ahead and get to work. So let's start by playing a little game. Right now, I am thinking of a sports team here in the United States. I would like you to tell me the probability that they will win the next game. What's your answer? Okay, I'll let you ask 4 questions, and what team is it is not allowed. Maybe you'll ask me, what sport is it? And I'll say baseball. What is the team's record right now? 90 wins and 67 losses. What is their opponent's record? 71 wins and 85 losses. Are they playing an away game or home game the next time? They're going to play a home game. Now, what is your estimation for winning? Do knowing these things help inform your decision as to whether or not they are more likely to win than they are to lose? So if I ask you, what is the probability of the team I'm thinking of winning, you might answer, well, it depends. So what we are really talking about here then is factoring in or taking into account several pieces of information. The outcome of winning in this case is influenced by other factors. Also, those factors may influence each other. So for example, the team I'm thinking of may win more during home games than away games. They do. They may have a better record against this team than they do on average. They do. So what is the probability? Is it greater than 50% that they might win this game? Well, if you take all these factors into account, and some of the factors that may influence each other, like they win more at home, then you would probably say they have a good chance of winning. So here are some more examples. Who performs better on the SAT test, men or women, overall? Now what if I ask you this way? Who performs better on the SAT test, men or women, if we look at verbal and math scores separately? So maybe overall, women do better than men. I don't really know, to be honest. But if we split that up into the math section and the verbal section, maybe it's not the same. Maybe women don't do better on both parts. Maybe men do better on the math part and women do better on the verbal part, which is usually historically true. So even though overall women do better, it's not even across the two sections. Which customer is more likely to default on their mortgage, those in Manchester or those in Bristol? So what if I ask you this? Which customer is more likely to default on their mortgage, those in Manchester or those in Bristol, if we break each city up into homeowners with a college degree and those without? So maybe one city or the other has a population that, for whatever reason, in the economic crisis, is more likely to default on their mortgage, unfortunately. But if we split those up into those with a college degree and those without a college degree, maybe it's not the same across both of those categories. And that's what we talk about when we're talking about two factors. So which city has more opportunity for workers, New Delhi or Mumbai? What if I ask you it this way? Which city has more opportunity for workers, New Delhi or Mumbai, if workers are separated into manufacturing, financial services, and energy production? So maybe overall, the work opportunity is better in Mumbai. But if we separate it out into another factor, manufacturing, financial services, and energy production, it's not even across those three categories. Maybe New Delhi is better in one of those three categories than the other two. And finally, which political party in South Africa gets more votes, the African National Congress or the Democratic Alliance? What if I ask it this way? Which political party in South Africa gets more votes, African National Congress or the Democratic Alliance, if the population is broken down into those 25 years old and younger and those 26 and older? So maybe the African National Congress wins the entire election, but if you break the voters down into two age groups, maybe the Democratic Alliance was more popular among the younger voters, I have no idea, than those that are older. So even though the ANC won the vote, it wasn't even across all age groups. And that's what we're talking about when we're talking about two factors and their interaction. So one that's really common, bad medicine. So let's say I take medicine A by itself and it's fine, it's good for me. I can take medicine B by itself. It's fine and it's good for me. What happens if I take them together? Uh-oh, we have a problem. We have a drug interaction, literally. So these two medicines might interact with each other to harm me. So on their own, they're safe, they're fine. But if you take them together, they may interact and harm you or harm me. And that's literally a drug interaction. So let's go ahead and review our problem from part 1 of our video on the Two-Way ANOVA. So you are a researcher interested in the effectiveness of 3 different cotton plant foods: Awesome Advantage, AA, Big Buds, BB, and Copious Cotton, CC. Now sometimes I will just say A, B, and C. Therefore, you design an experiment in which you will test each plant food, AA, BB, and CC, with 1 feeding per day and 2 feedings per day for 75 days after planting. 8 plants will be tested for each combination. The variable of interest is the plant's height in centimeters. So we're going to see if any of these 3 different plant foods creates difference in plant height and whether or not feeding them once per day or twice per day affects the plant height. So we're looking at two factors, plant food and the frequency at which they are fed. Now we're going to use the same type of cottonseed just to eliminate that variable. So we do that, and here is some data we come up with. So we can see that for plant food AA, we have those there in the red. For plant food BB, we have those 16 plants there in the blue. And for plant food CC, we have those 16 plants there in the green. Now, those are our three plant foods. Now we also have two feeding frequencies. So we have the one feeding, which is the top row, and then the two feedings, which is the bottom row. So you can see that each combination of plant food and feeding has 8 plants in each one. So this is a two-factor ANOVA with replication, because we have 8 plants in each combination. Now if we go ahead and take our cell means, this is what we come up with. So plant food AA with one feeding had an average height of 60 centimeters. Plant food BB with one feeding had an average height of 62.5 centimeters. Plant food CC with one feeding had an average height of 57.5 centimeters. Now overall, the one feeding row had an average height of 60 centimeters. Now the same thing for our two feedings. So for AA it was 67 centimeters, for BB it was 67 centimeters, and for CC it was 40.5 centimeters. Now each plant food also has its own mean. So for all the plants that were fed with plant food AA, both one feeding and two feedings, the average was 63.5 centimeters. All 16 plants that were given plant food BB had an average height of 64.75 centimeters, and all 16 plants that had plant food CC had an average height of 49 centimeters. And overall, our mean was 59.09. So all those plants, every plant we ever measured, as a group, had an overall mean of 59.09 centimeters. Now it's important to remember here that when we make a table of means like this one, the values are not individual data points. They are all cell means, in this case a mean of 8 plants or 8 measurements, with their own distribution. So each one of these cells, because it's made up of 8 measurements, has its own unique distribution. So in a two-way ANOVA, the way these distributions fit together, kind of like a puzzle, is at the very heart of the technique. It's all about the way the distributions fit together. So let's plot these cell means on a graph. So again, this is what we're talking about in this video, a graph of marginal means. So SPSS generates this graph. So we can see here that we have 2 lines, and along the bottom we have our 3 plant foods. We have Awesome Advantage AA, Big Buds BB, and Copious Cotton CC. Now each line represents the number of feedings that were given per day. So the blue line is the one feeding per day line. So you can see it's relatively flat as it kind of goes across the middle of the graph. Now the 2 feedings per day line is the one in green. So we have sort of a high measurement, a high mean, and then we go way down to a little bit above 40 there. So that's the 2 feeding line. So here are some questions we need to ask. For Awesome Advantage Plant Food AA, how many feedings produce more growth? Well, if we look at our graph, we can see that it appears that 2 feedings per day produced more growth. What about for Big Buds, or BB? How many feedings produced more growth? Well, again, it appears that the 2 feedings per day produced more growth. Now, what about for Copious Cotton, or CC? Well, this one's the opposite. In this case, it appears that the 1 feeding per day produced the most growth. And that's interesting. So we ask ourselves, do 2 feedings per day produce more growth across all plant foods consistently? Well, no, it doesn't. It appears that 2 feedings are better for plant food AA and BB, but not for CC. This type of situation is called an interaction. So an interaction occurs when the effect of one factor changes for different levels of the other factor. So in this case, the growth changed. It was 2 feedings per day were better for AA and BB, but when we got to CC, it wasn't. It changed. So in this case, the most effective feeding frequency changes across plant food types. So if there was no interaction, what would this look like? Well, we would expect that the green line would always be above the blue. Or if for some reason one feeding was better, the blue might be completely above the green. But the lines would not cross. So in a marginal means graph, as a general rule, we look to see if the lines cross or would cross, because that tells us that the factors change, their values change across the groups. So here is our table of marginal means. We already looked at that. Here is our marginal means graph we just talked about in the previous slide. And here is the SPSS output. Now you notice I highlighted a certain part of it, and that's because we always look for a significant interaction first. That's always where we start. So you can see in the SPSS output we have several things. Now we're really interested in 3 of them. We're interested in feedings, plant food, and feedings by plant food, or feedings time plant food. That's our interaction. So we always look at the interaction first. Now if we go across that row, we will see that we have an F statistic of 9.333 and a significance value of 0.000. Well, what does that tell us? That tells us that the interaction between these 2 factors is significant. And of course, if we look over at our graph, that should be readily apparent. So if we do a marginal means graph and it looks something like we see here on the right, we would expect the interaction to be significant when we actually do the analysis. So we can see the relationship between these 3 things here. We have our table of marginal means in the lower left, we have our marginal means graph over here on the right, and then we can actually see the output in SPSS over here on the left. Again, always checking the interaction term first.